Electrons in the atom. Atoms interact with each other through their electrons. This is why almost all the properties of the elements except mass are due to electrons. Chemical bonds involve only electrons, so electrons determine how atoms combine into compounds. We find a rich variety of matter because electrons inside atoms are organized in unusual and complex patterns. Exactly how electrons create the properties of matter was a puzzle that took bright scientists a long time to figure out. Almost all the light you see comes from atoms. For example, light is given off when electricity passes through gas in a fluorescent light bulb or a neon sign. When scientists look carefully at the light given off by a pure element, they find that light does not include all colors. Instead, they see a very few specific colors, and the colors are different from different elements, figure 1311. Hydrogen has a red line, a green line, a blue line, and a violet line in a characteristic pattern. Helium and lithium have different colors and different patterns. Each different element has its own characteristic pattern of colors called a spectrum. The colors of clothes, paint, and everything else around you come from this property of elements that allow them to emit or absorb light of only certain colors. Each individual color in a spectrum is called a spectral line because each color appears in a line in a spectroscope. A spectroscope is a device that spreads light into different colors. The illustration below shows the spectroscope made with a prism. The spectral lines appear in the screen at the far right. In Chapter 10, you learned that light is a form of pure energy that comes in tiny bundles called photons. The amount of energy in a photon determines the color of the light. Red light has lower energy and blue light has higher energy. Green and yellow light have energy between red and blue. The fact that atoms only emit certain colors of light tells us that something inside an atom can only have certain values of energy. Danish physicist Niels Bohr proposed the concept of energy levels to explain the spectrum of hydrogen. In Bohr's model, the electrons in a hydrogen atom must be at a very specific energy level. You can think of energy levels like steps on a staircase. You can be on one step or another, but you cannot be in between steps because, except in passing, electrons must be in one energy level or another and cannot remain in between energy level. Electrons change energy levels by absorbing or emitting light. When an electron moves from a higher energy level to a lower one, the atom gives up the energy difference between the two levels. The energy comes out as a different color of light. The specific colors of light spectral lines correspond to the differences in energy between the energy levels. The diagram below shows how the spectral lines of hydrogen come from electrons falling from the third, fourth, fifth, and sixth energy levels down to the second energy level. Quantum theory says that when things get very small, like the size of an atom, matter and energy do not obey Newton's laws or other laws of classical physics. That is, the classical laws are not obeyed in the same way as with larger objects like a baseball. According to the quantum theory, when a particle such as an electron is confined to a small space inside an atom, then the energy, momentum, and other variables of the particle become restricted to certain specific values. You are used to thinking of a particle like a grain of sand. A sand grain is small, but you can easily imagine it has definite shape, size, position, and speed. According to quantum theory, particles the size of electrons are fundamentally different. Instead, when you look closely, an electron is smeared out into a wave-like cloud. There is no exact position where the entire electron is. If an electron is spread out into a cloud, how can you locate its exact position in an atom? You can't. The work of German physicist Werner Heisenberg led to Heisenberg's uncertainty principle. According to the uncertainty principle, a particle's position, momentum, energy, and time can never be precisely known. The uncertainty principle arises because the quantum world is so small. To see an electron, you have to bounce a photon of light off it or interact with the electron in some way, figure 1313. Because the electron is so small, even a single photon moves it and changes its motion. That means the moment you use a photon to locate an electron, you push it so you no longer know precisely how fast it was going. In fact, any process of observing in the quantum world changes the system you are trying to observe. The uncertainty principle exists because measuring any variable disturbs the others in an unpredictable way. The positive nucleus attracts negative electrons like gravity attracts a ball down a hill. The farther down the hill an electron slides, the less energy it has. Conversely, electrons have more energy farther up the hill and away from the nucleus. The higher energy levels are farther from the nucleus and lower energy levels are closer. Bohr's model of electron energy levels was incomplete. Electrons are so fast and light that their exact position within an atom cannot be defined. Remember, in the current model of the atom, we think of the electrons in an atom as moving around the nucleus in an area called the electron cloud. The energy levels occur because electrons in the cloud are at different average distances from the nucleus. Inside an atom, electrons always obey these rules. The energy of an electron must match one of the energy levels in the atom. Energy level can hold only a certain number of electrons and no more. As electrons are added to an atom, they settle into the lowest unfilled energy level. Energy levels are predicted by quantum mechanics, the branch of physics that deals with the microscopic world of atoms. While quantum mechanics is outside the scope of this book, you should know that it is a very accurate theory and explains energy levels. The first energy level can accept up to 2 electrons. The second and third energy levels hold up to 8 electrons each. The fourth and fifth energy levels hold 18 electrons, figure 13-14. A good analogy is to think of the electron cloud like a parking garage in a crowded city. The first level of the garage only has 2 spaces for 2 cars, just as the first energy level only has 2 spaces for 2 electrons. The second level of the garage can hold 8 cars, just as the second energy level can hold 8 electrons. Each new car that enters the garage parks in the lowest unfilled space, just as an additional electron occupies the lowest unfilled energy level. The number of electrons in an atom depends on the atomic number, because the number of electrons equals the number of protons. That means each element has a different number of electrons and therefore fills the energy levels to a different point. For example, a helium atom has 2 electrons, figure 13-15. The 2 electrons completely fill up the first energy level, diagram below. The next element is lithium with 3 electrons. Since the first energy level only holds 2 electrons, the third electron must go into the second energy level. The diagram shows the first 10 elements which fill the first and second energy levels. Please take a moment to answer these questions.